three things. In graph theory, an adjacent matrix is a matrix derived from a graph that carries the information about whether there is an edge or there is not an edge between some particular two nodes. So it is a square matrix, and it records the information about the graph. Basically, it's an alternative way of writing down the graph, because the graph, what it contains is the information of the nodes and about whether there's an edge between some particular nodes, and perhaps if there's a direction of that edge. So a lot of this information can be put into the matrix. So we will be looking at some examples, let's say 2-3 examples of how to take a graph and get the adjacent matrix about it. First, let's take a general example which doesn't have any sort of tricks. That means some undirected simple graph. And let's take a triangle, complete graph like this, 1, 2, 3. Any two different nodes are connected. So 1, 2, and 3 are the three nodes, and we see there's an edge, and those edges don't have a direction. Now, what does the matrix say? It takes any two nodes, even a node with itself, which there won't be any edges it has with itself, because there will have to be a loop, and a simple graph doesn't have loops. So we take this graph and we look at it, and we create a square matrix. By the way, adjacent matrix will be a square matrix, and the matrix has the same amount of rows and columns as the initial graph had nodes. So 3 nodes means it will be a 3x3 matrix. 5 nodes, if there were 5, now here are 3, there were 5, it will be a 5x5 matrix, and by a square matrix. Now, the rows are from which node we go, and the columns are to which row we go, as far as locating a particular entry in that matrix, and then evaluating that entry or giving a value to that entry based on the information. And the information is as follows. If there is an edge between the two nodes, then that entry corresponding to that entry, then the value that will be given to that entry that corresponds to those two nodes, and the question about them, whether there is an edge between them or not, will have a value of 1 if there is an edge, and a value of 0 if there is no edge. So that's that. So let's see. Now, if it's a directed graph, it will only have a value of 1 if it's the right direction. If it's the opposite direction, it will also have a value of 0. We'll see that in a second. So let's see. So this 3-node graph will create a 3x3 adjacent matrix. And I'll say it's every entry can be seen as A sub ij, where I is the number of the row, which it goes like here, like this, down, up from up to down, and the number of a column is the j, and it goes from the left to the right. We'll see. Basically, what it means is, I'll just write these helping numbers here so we can orientate ourselves. Now, what that means is, if I want to see in undirected graph, it doesn't matter, because an edge from 1 to 1 is the same as edge from 1 to 1. 2 to 3 is the same as 3 to 2. Because there's not a direction at the edge. If it was a directed graph, which we'll look at in a second, it will matter. So we'll actually end up, there will be some replicated information in this matrix, but we'll deal with it. That's not a problem. Let's see. So basically, I want to see through that entry, is there an edge between some two nodes? So if I want to see, is there an edge between 1 and 2? I see the first row and the second column. This is the order in which we locate it. So an edge from 1 to 2 is going to be, is there an edge? The answer is going to be answered by if there's an edge from 1 to 2, it's going to be answered by the first row and the second column entry, which is this one. And yes, there is, so there will be given a 1. So if there is, there's a 1. If there is not, there's a 0. Now, the opposite direction from 2 to 1 will mean I have to start with the second row and go to the first column, which will be this location. But now, is there an edge from 2 to 1? There is also. So here we already see the symmetric nature. But that is so with the undirected graphs. With the directed graphs, it can be just in one direction. It means we would say the edge goes from 1 to 2, but it doesn't go from 2 to 1. But we'll see that in a second. For the undirected one, it goes as follows. So from 1 to 1, let's say, this is the entry that says from the node 1 to the node 1, which is not even two different nodes, it's the same one. From the same one to itself, that would only be 1 or 2, depending on the notation choice. By the way, there's a notation choice. So for now, we don't have any loops. For that reason, there's no edge connecting 1 to itself. It means 1 has a 0, because when there is not an edge, it's a 0. 2 to 2 is also a 0, and 3 to 3 is also a 0. Now, there's nothing connecting those to themselves, so that's why the whole diagonal, which holds the information about the nodes to themselves, do they have an edge or not, has zeros as values, all the diagonal values. And the reason for that is because they don't have any edge connecting themselves to the node to itself. And that would happen if there was a loop. If there is a loop, usually, but it can also be switched. The notation goes as follows. If there is a loop on the graph, and we'll see it in the next example perhaps, if there is a loop and the graph is directed, the value in that particular entry, and there's a loop, one loop at that node, that will give a value of 1 for that node, that there is an edge going to itself. If we're asking about the entry of whether if that node is connected by an edge to itself. If it's an undirected graph, more often it might be given a value of 2. So that's the notation choice, but it can be switched, it's used differently. Different people use it differently, but generally let's say if it's a directed graph, the value for a loop will be 1 if we're asking about the connection to itself, and 2 in the case of an undirected one. So if we had a loop here, for example, 3 to itself, I would give a 3 and 3 a 2, but we don't have it. 3 to 1 there is, and 1 to 3 because undirected, as already mentioned, is also 1 because that's the same. And 3 to 2, third row and second column always is order. 3 to 2 is 1, and 2 to 3 is also 1, the same, undirected. So this is our first graph. Now we see, this is a complete graph. And a complete graph is quite general, and when one knows it, one can very quickly get the adjacent matrix. Why? It's because we know that if there's no loops, the zero diagonal will be there always. And if there is no repeated edges or no loops, it also means that and everything is connected to any other non-same node. Every node is connected to a node that is not itself. Then it's a complete graph, and all the other ones will be ones. But even if it wasn't a complete graph, we will still have a symmetry. Maybe we would have to at least find the whole one side, let's say below the zeros, and from that we'll derive the upper side directly. With this one, we didn't even have to do that. We just knew that the diagonal is zeros and all the other ones are ones because it's a complete graph. But if it wasn't complete, let's say it was this, then what would it mean? It would mean basically that there's nothing between 2 and 3. So 2 to 3 there will be nothing, and 3 to 2 there will be nothing. So these two would be 0, but we see the symmetry is still kept. The symmetry is basically based on the diagonal, so there's a 0 or 0, if we read from the other side it's also 0, 0. So that's that. And that could happen also here, here, and so on. Right? So that's that. I changed it slightly, and now again, this is a concrete, correct description of that. 3 to 2 just to check it, and 2 to 3. 2 to 3, like that. So these will now suddenly have 0 because there's no edge there. I removed it. But still we see undirected graph, and it is therefore symmetrical as a matrix. The adjacent matrix will be symmetrical. Now let's look at another example with a directed graph, and also it will have loops. So as I said, a directed graph, when it has loops, usually it's chosen that the value given if there's a loop on that node will be 1. So let's see an example. So right. Yeah. So let's choose, for example, this one. It's one more. Then I also name the nodes like this, and let's say one has a node to itself, an edge to itself, so a loop. So one will have to itself some value, namely 1. Here will be a 1. So now the number of nodes defines the size of the matrix. 4 nodes means a 4 by 4 matrix. And again, when we go from a node, it's from this 1, 2, 3, 4, the numbers we're using. It's from the row sphere, and then to finalize the finding of that particular entry, we go to the column number also. That's to where we go, to which node we go in that edge that we are asking, is there such an edge or not? 1, 2, 3, 4. So from 1 to 1 will be this. From 1 to 2 is here, but from 2 to 1 is here. From 2 to 1 is here. From 3 to 4 is here, but for 4, from 4 to 3 is here. So that's that. We'll fill it out now. So basically, now it's directed. Now it won't necessarily be symmetrical here, and the reason is because just because there is an edge from 2 to 3 doesn't guarantee there's an edge from 3 to 2. And actually, we don't have like everything is directed, and each edge is there like one. So if there's one direction, the other one is not there. This whole graph is as follows. So let's do it. So just to make it clear, these numbers are not inside the adjacent matrix. These are just helping me to identify individual locations, because one could lose track of the individual entries because there's free space now. We'll be filling it out like this. So let's first do 1 to 2. Is there something? There's nothing at all. There's not even from the other side, the directed one. So there's nothing. So 1 to 2 has nothing. 1 to 1 though has something. We will skip that one. 1 to 1 has something. As I said, if it's directed one, usually for the loop there's a number of 1 as a value. 1 to 3, is there something? No, because it's just from 3 to 1, so there's nothing in that direction. 1 to 4, yes, there's 1. And the same way I fill out the rest. So we saw that 1 to 3 has nothing, but 3 to 1 will have, because the arrow points in the direction of the 1. So 3 to 1 will be this entry, and there will be a 1 there. But that's skipping. Let's do the second line first. So 2 to 1 is 2 to 1, there's nothing at all. 2 to 2 itself is 0, nothing. There's no loop for 2 around 2. 2 to 3, it's from the other direction. And 2 to 4, yes, there is. 3 to 1, there is. 3 to 2, there is. 3 to 3, there is no loop. 3 to 4, there is from the other side. So 3 to 4 is from the other side. And then 4 to 1, so that's from the other side. 4 to 2, it's from the other side. 4 to 3, it's right, and 4 to 4, there's no loop. So that's the result we have for the adjacent matrix of this one. So basically, to sum it up, an adjacent matrix, when we have a graph, and we dealt here with a simple graph, undirected here, and here we dealt with not even simple one. It has a loop here and it's directed. So for both of those, we can devise some rules and get the adjacent matrix. And the adjacent matrix, basically, it records the information whether if between two nodes, either a node to itself or two different distinct nodes in that graph, is there an edge between them. And also in the directed one, it's only counted if the direction matches, where the direction is always taken according to the entry. So 2, 1, which is this entry, means is there an edge from 2 to 1, and 1, 2 means is there an edge from 1 to 2. So that's the difference. In this case there is neither, because there's no edge at all, but in the other cases we saw that pattern. So generally an adjacent matrix records information about if there is an edge between the nodes, it will get a 1, and if there's not an edge, it will get a 0.